Lewis, I've been thinking about something wild. What would actually happen if we took humanity's most powerful nuclear weapon and detonated it at the deepest point of the ocean?
Ah, the classic doomsday scenario. Most people immediately jump to catastrophic conclusions. They imagine tsunamis hundreds of meters high destroying coastal cities, earthquakes leveling entire countries, new volcanoes erupting everywhere and bringing us nuclear winter. Some even wonder if Earth itself could be ripped apart or thrown out of orbit.
Right, that's exactly what I was picturing. Giant waves, massive destruction everywhere.
Well, hold on. The reality is quite different. Almost the opposite, actually. But to understand why, we need to talk about where exactly we're setting this thing off. You familiar with the Mariana Trench?
That's the deepest part of the ocean, right?
Exactly. Currently, Earth's deepest known point is inside the Mariana Trench. Picture this. It's a very deep valley sitting right at the edge of two tectonic plates. The whole thing looks like an upside-down mountain. It reaches a depth of about 11 kilometers.
Wait, 11 kilometers down?
Yes, that's almost 3 times deeper than the dark grave of the Titanic. Think about that for a second. It's one of the last places on Earth for humans to explore. Down there, it's pitch black. The pressure is 1,000 atmospheres. And because humans haven't really touched it, it's a relatively pristine environment.
Sounds like the perfect place for our nuclear test, I guess?
Exactly what I was thinking. Now, we're not going to use just any bomb. We'll use the most powerful nuclear bomb humans have ever exploded, the RDS-220 hydrogen bomb, better known as Tsar Bomba.
How powerful are we talking?
This thing was absolutely massive. Its explosion was so huge that its shockwave traveled around the Earth 3 times. 3 complete times around the planet. And its mushroom cloud? It stretched 56 kilometers into the sky. The shockwave was strong enough to destroy everything in 1,000 square kilometers. The fireball was hot enough to burn all the rubble left behind.
That's insane.
Here's the thing about bombs like this. They release such an enormous amount of energy all at once that they could literally boil away an entire lake. And if we set off a nuclear bomb in the Mariana Trench, that's exactly what starts to happen.
Starts to happen?
Yeah, I chose those words carefully. Let me walk you through it. Let's pull the trigger. In the first few microseconds, the nuclear fuel undergoes its chain reaction and explodes with the power of 50 megatons of TNT.
50 megatons.
A blinding flash of light illuminates the darkness of the trench for the first time in history. The heat of the explosion produces what we call a cavity, basically a flaming bubble made of water vapor, radioactive nuclei, and the remains of some very unlucky fish.
Poor fish.
This bubble grows quickly as it vaporizes the water around it. The pressure of the bubble is immense, absolutely immense. It plows outwards as if there's nothing in the way, sending off a shockwave that'll be felt by seismic stations and whales around the world.
So that sounds pretty destructive so far.
And then, almost as fast as it emerges, it stops.
It stops? What do you mean it stops?
This is where it gets really interesting. See, on the surface of the Earth, this fireball bubble would grow to 10 kilometers across the second after it's detonated. The atmosphere barely puts up a fight to hold it back up there. But Max, remember where we are.
The bottom of the Mariana Trench.
Exactly. The pressure at the bottom of the Mariana Trench is enormous. We've got 11 kilometers of water overhead. Being in the Mariana Trench is like being crushed by a hydraulic press from every direction at once.
So the water pressure is fighting back against the explosion?
Precisely. Here, a second after the detonation, our bubble is about 1 kilometer across. And then, oddly enough, it actually starts to shrink.
The explosion shrinks?
Yes, the bubble overextends itself. It loses pressure as it expands until the water turns it back, recompressing it. Think of it like a tug of war between the fiery death bubble and the water. This goes back and forth a few times, the bubble shrinking and growing, shrinking and growing.
But eventually one side wins?
Eventually, the bubble loses for good. The pressure around it is just too great. Turbulent water begins to chop it up. It becomes something like the underwater equivalent of a mushroom cloud as it disintegrates into many smaller, hot and radioactive bubbles that start drifting upwards.
So what happens when all those bubbles reach the surface?
And here's the anticlimax. As our mighty destructive blast rises to the surface, it does basically nothing.
Nothing?
Just a small wave and a bubbling plume of radioactive warm water in the Pacific. That's it.
But what about the massive tsunamis you mentioned at the start? Japan? California?
No tsunami will wash away Japan or California. Although, I'll admit, boats and whales in the immediate area might have a bad time. The radioactive fallout will be diluted into the Pacific after a few days. Now, a fair amount of radioactive water and salt does make it to the atmosphere, where it collects, and then rains down again.
That sounds dangerous.
Even if the wind blows the fallout directly towards the Philippines, the worst of it probably happens over the oceans. It's not good, but it's not the apocalypse people imagine.
Okay, but what about earthquakes and volcanoes? Those are triggered by pressure changes, right? Surely a massive explosion at the bottom of the ocean would trigger those.
Ah, yes, most people ask about that. The real danger comes from our explosion triggering earthquakes and volcanoes, right?
Exactly.
Even if we detonated the bomb right in the trench at the exact point where tectonic plates touch, probably not.
Probably not? That's a pretty big bomb going off right where the plates meet.
Here's why. The explosion would vaporize a part of the seafloor. It would turn a lot of sand into glass. But most of the energy goes into the water, not into seismic waves. That's the key point. The water absorbs most of the energy.
But wouldn't any seismic energy at a tectonic boundary be dangerous?
Think about this. Earthquakes are already quite common at tectonic plate boundaries. This isn't some stable, quiet area. And earthquakes with as much seismic energy as our bomb happen a few times a year without triggering any sort of apocalypse.
Okay, I can see that. But earlier you mentioned Earth being thrown out of orbit. Could the explosion affect Earth's orbit at all?
No. Since no mass is taken away or added to the Earth, our orbit is completely unaffected. Zero change.
But that's a huge amount of energy. Surely it has some effect.
Look at it this way. There have been well over 1,000 nuclear tests in the last 70 years. 1,000! And that didn't change our orbit at all. So why would this time be different?
I guess when you put it like that.
Here's the fundamental truth, Max. The strongest forces humanity can unleash are laughable compared to the forces of nature. Absolutely laughable. The planet is too big. It doesn't care about our weapons.
So let me make sure I understand this. We take the most powerful weapon humanity has ever created. We detonate it at the deepest point of the ocean, at the boundary of tectonic plates. And what happens to us?
Pretty much nothing.
That's kind of humbling, isn't it?
It really is. We like to think of ourselves as these powerful beings capable of reshaping the planet. And in some ways we are. We can certainly affect our environment and climate, but when you put our most powerful weapons against the raw forces and scale of the Earth itself, we're nothing. The planet has survived asteroid impacts that make nuclear weapons look like firecrackers.
I suppose all those disaster movies got it wrong, Ben.
Completely wrong. They make for exciting entertainment, but the physics just doesn't support it. The ocean is too big, too deep, too powerful. It just absorbs the blast, contains it, and moves on like nothing happened. Sure, you'd have some local damage, some radiation, some dead sea life in the immediate area. But global catastrophe? Not even close.
What about the fish and other sea creatures down there? You mentioned them earlier.
Oh, everything in the immediate blast zone is definitely toast. The flash vaporizes them instantly. And creatures in a wider radius would be killed by the shockwave or cooked by the heat. The radioactive bubbles rising up would contaminate and kill more marine life along the way. It would be an environmental disaster for that specific area of the ocean, no doubt about it.
How long would that area remain dangerous?
The initial radioactive contamination would be pretty severe in the immediate zone. But remember, we're talking about the Pacific Ocean, the largest body of water on Earth. The dilution effect is massive. Within days to weeks, most of the radioactive material would be spread out and diluted to much lower concentrations. It's still not great, and you wouldn't want to eat fish from that area for a while, but it's not a permanent dead zone.
And the pressure down there really makes that much difference?
The pressure makes all the difference. That's the entire story here. At sea level, an explosion like this can expand relatively freely. The air doesn't push back very hard. But 11 kilometers down, every cubic centimeter of that bubble is fighting against incredible pressure. It's like trying to inflate a balloon while someone's standing on it. Actually, more like while 1,000 people are standing on it.
That's a great way to put it.
And that pressure doesn't just stop the bubble from expanding, it actively crushes it back down. The water at that depth is so dense, so heavy, that it basically suffocates the explosion. The bomb releases all its energy, sure, but that energy just can't go anywhere dramatic. It gets contained, compressed, and ultimately dispersed into the surrounding water as heat.
So, in a weird way, the ocean is protecting us from our own weapon.
Exactly. The ocean acts like a massive shock absorber. All that energy that would create devastation on land just gets absorbed and distributed throughout billions of gallons of water. The ocean has so much thermal mass that even a 50 megaton explosion is just a drop in the bucket. Well, a very hot, radioactive drop, but still just a drop.
What would it look like from the surface? Like if you were on a ship a few kilometers away?
Great question. You probably see the water suddenly bulge upward as the pressure wave reaches the surface. Then you'd see this massive bubbling and churning as all those smaller radioactive bubbles break through. The water would be steaming, creating a huge plume of vapor and spray. And you'd see this eerie glow from the radioactive material. But no massive wave rushing toward you, no wall of water, just this violent, bubbling cauldron that would gradually calm down.
Would you hear anything?
Oh, absolutely. The shockwave would create a sound that would travel through the water for thousands of kilometers. Submarines and whales would detect it instantly. Ships would feel a jolt, not enough to sink them if they're far enough away, but definitely enough to notice. It would sound like a deep, rumbling boom that seems to come from everywhere at once. Seismic stations around the Pacific would light up with readings.
You mentioned earlier that the shockwave would be felt around the world?
Yes, seismically. The energy that does make it into the Earth's crust would travel as seismic waves. Scientists monitoring seismographs in Japan, Hawaii, California, even on the other side of the planet, would see the signature of the explosion. They'd be able to pinpoint exactly where it came from and roughly how powerful it was. It's the same way we detect underground nuclear tests.
But that seismic energy wouldn't trigger earthquakes in those distant places?
No, seismic waves from an explosion just pass through. They're detected, they're measurable, but they don't have the right characteristics to trigger earthquakes elsewhere. Earthquakes happen when stress that's been building up along a fault line is suddenly released. Our explosion might add a tiny bit of stress, but nothing compared to the tectonic forces already at work. It's like flicking a tight rubber band versus pulling it to its breaking point.
So even at the tectonic plate boundary, we're not adding enough stress to matter?
Exactly. Those plates are under constant, enormous stress from the movement of the Earth's crust. We're talking about forces built up over years, decades, sometimes centuries. Our bomb goes off in a fraction of a second. The energy release is impressive by human standards, but in geological terms, it's a blip. A tiny, momentary addition to forces that are thousands of times larger and more sustained.
We really aren't as powerful as we think we are we?
Not even close. And honestly, that's kind of reassuring in a way. It means that even our worst weapons, even our biggest mistakes, can't literally destroy the planet. They can devastate our civilization, absolutely. They can cause tremendous human suffering and environmental damage. But break the Earth apart? Knock it out of orbit? Not happening.
I guess the real danger of nuclear weapons isn't to the planet. It's to us.
Now you're getting it. The danger has always been to human civilization, to our cities, to our populations. A nuclear war wouldn't destroy Earth. Earth has survived much worse. But it could definitely destroy us, and much of the life we depend on. That's the real horror of these weapons. Not planetary destruction, but human destruction.
That's actually more sobering than the disaster movie version.
It is, because it's real. The planet will survive us. It's survived 5 major mass extinctions. It's been hit by asteroids, covered in ice, boiled in volcanic eruptions. Life always finds a way to bounce back. But we're fragile. Our civilization is fragile. And that's what we should actually be worried about protecting.
Going back to the ocean for a second, you said the fireball would be about a kilometer across after a second?
Yes, about a kilometer, which sounds huge, and it is. But remember, on the surface, it would be 10 kilometers across in the same time frame. The pressure reduces its size by about 90, and then it starts shrinking from there as the pressure overcomes the expansion.
What's happening inside that bubble during all this?
Inside the bubble, it's hell. Absolute hell. The temperature is millions of degrees initially, hotter than the surface of the sun. The pressure inside is tremendous, fighting against the outside pressure. You've got superheated steam, plasma from the vaporized water and bomb materials, radioactive particles flying around at incredible speeds. It's a miniature star burning underwater.
And it's just shrinking and growing?
Yes, it's this violent oscillation. The bubble expands, overshoots, runs out of pressure, then the ocean crushes it back down. That compression heats it up again, gives it another burst of energy, and it expands again. Each cycle is smaller than the last as energy bleeds off into the water. Eventually, the oscillation stops and the bubble just breaks apart.
How long does this whole process take?
The main oscillations, maybe a few seconds. The rise to the surface depends on where the fragments end up, but you're looking at maybe a minute or two for the fastest bubbles to reach the surface from 11 kilometers down. The whole visible event from detonation to surface disruption is probably over in under 5 minutes.
That's it? 5 minutes and it's done.
The visible part, yes. The radiation lingers longer, obviously, and the heat added to that water will take time to dissipate. But the explosive event itself? Very brief. That's the nature of explosions. They're incredibly short-lived events. All that energy released in an instant. Then, it's just about watching the consequences unfold.
What about the glass you mentioned? The sand turning to glass?
Oh, right! So when sand is exposed to extreme heat, and we're talking thousands of degrees, the silica in the sand melts. Then, it cools rapidly in the cold ocean water and forms glass. We'd create this weird glass crater on the seafloor. It's called trinitite when it happens at nuclear test sites on land. Underwater, you'd have this bowl-shaped glass formation with radioactive particles trapped inside.
Would it stay there? Like a permanent marker of the explosion?
For a while, yes. Eventually, ocean currents would cover it with sediment, sea life would grow on it, and it would become part of the seafloor geology. But if someone went down there decades later with a submersible, they could probably still find it. It would be this bizarre artifact, a perfectly smooth glass crater in the middle of natural rock and sand.
You know, when you describe it all piece by piece, it's clear why nothing catastrophic happens. But it's still kind of counterintuitive.
It absolutely is. Our intuition is built from our experience on land, in air, at normal pressures. We have no intuitive feel for what 11 kilometers of water pressure means. We've never experienced anything like it. So our brains just extrapolate from what we know. Big bomb equals big destruction. But the physics tells a different story.
I bet a lot of people would be disappointed by this outcome.
Oh, definitely. It's not as exciting as Hollywood would have us believe. No dramatic tsunami racing toward shore, no earthquakes toppling buildings, no fiery apocalypse. Just some bubbles, some radiation, and the ocean basically shrugging it off. But honestly, that's the beautiful part. Nature is more powerful than our weapons. That's actually comforting.
It really is. So, if someone asked you to summarize this whole thing in one sentence?
I'd say, we detonated the most powerful weapon humanity has ever created in the deepest place on Earth, and the planet barely noticed. That's the ultimate truth here. For all our power, for all our technology, for all our capacity for destruction, the Earth is bigger. The ocean is stronger. The forces of nature dwarf anything we can do.
That's actually kind of poetic.
I suppose it is. But it's also just physics. Cold, hard, beautiful physics. The same physics that governs supernovas and black holes also governs what happens when we set off a bomb underwater. The scales are different, but the principles are the same. Energy, pressure, thermodynamics. They don't care about our expectations or our fears.
Thanks for walking through all of this. I have a much better understanding now.
That's what I'm here for. And remember, next time someone tells you about some doomsday scenario, ask yourself, does the physics actually support this? More often than not, reality is far less dramatic than fiction. But that doesn't make it any less interesting.